Picture the universe empty, silent, and impossibly vast, a place where distances are measured in light years and mysteries lurk in every shadow. But among the countless celestial wonders, few are as extreme, as enigmatic, or as downright strange as neutron stars. These cosmic powerhouses pack the mass of an entire sun into a sphere no bigger than a city. They spin faster than a blender, warp space-time like a cosmic whirlpool, and are so dense that a single teaspoon of their material would weigh billions of tons back on Earth. And yet, despite their mind-bending nature, neutron stars remain some of the most distant and least understood objects in the cosmos. What makes them even more fascinating? They're not just scientific curiosities, they're time capsules, messengers from the darkest corners of space. Some are so old they've been spinning since before our solar system was born. Others erupt with bursts of energy so powerful they can be detected halfway across the universe. And then there are the ones that defy explanation altogether, stars with magnetic fields a quadrillion times stronger than Earth's, or those that vanish without a trace, leaving astronomers scratching their heads. The deeper we look, the more questions they raise. How do they form? What happens inside them? And why do some of them seem to break the laws of physics as we know them? That's exactly what we're diving into today, 30 incredible facts about the universe's most distant neutron stars. We'll explore how these extreme objects rewrite the rules of reality, from their explosive births in supernova to their eerie, lighthouse-like beams that sweep across the cosmos. You'll discover how they help scientists test Einstein's theories, why they might hold the key to understanding dark matter, and even how they could one day serve as interstellar GPS for future space travelers. So buckle up, because we're about to journey to the edge of known physics, where the universe gets weird and neutron stars reign supreme. The birth of a neutron star is one of the most violent events in the universe, a cosmic spectacle where an entire star's life ends in a cataclysmic explosion. When a massive star, at least 8 times heavier than our Sun, exhausts its nuclear fuel, its core collapses in on itself in a fraction of a second. The outer layers rebound off this collapsing core in a shockwave so powerful it rips the star apart, a supernova so bright it can outshine entire galaxies for weeks. But deep inside that chaos, the core keeps collapsing, squeezed by gravity until protons and electrons are forced together, merging into neutrons. What's left is a neutron star, an object so dense that if you could scoop up a single sugar cube's worth of its material, it would weigh as much as Mount Everest. Think about that for a second. The pressure inside a neutron star is so extreme that atoms can't even exist in their normal form. Instead, matter gets crushed into a sea of neutrons packed tighter than anything else in the known universe. It's like taking all the cars, skyscrapers, and mountains on Earth and compressing them down to the size of a marble. And yet, despite this unimaginable density, neutron stars aren't just lifeless husks. Some spin hundreds of times per second, sending out beams of radiation like cosmic lighthouses. Others have magnetic fields strong enough to atomize you from thousands of miles away. Their formation is both an ending and a beginning, the death of a star, giving rise to one of space's most bizarre and fascinating objects. But here's what's even wilder. Neutron stars don't just defy our everyday intuition about how matter behaves, they push the limits of physics itself. The conditions inside them are so extreme that scientists still don't fully understand what happens to matter under that kind of pressure. Some theories suggest the cores might contain exotic states of matter, like quark soup, or even stranger particles that don't exist anywhere else. Every time we discover a new neutron star, it's like uncovering a cosmic laboratory where the universe tests its own rules under conditions we could never replicate on Earth. If you thought the birth of a neutron star was extreme, wait until you hear how they behave afterward. Some of these cosmic relics don't just sit quietly in space. They spin at speeds so mind-boggling they'd make a jet engine look sluggish. Meet pulsars, neutron stars that rotate hundreds of times every second, flashing beams of radiation across the cosmos like a lighthouse on overdrive. The fastest known pulsar, named PSR-J 1748-2446 AD, whips around a staggering 716 times per second, so fast that its surface moves at roughly a quarter the speed of light. Picture a blender spinning so violently it could puree a planet, or a skater pulling in their arms mid-spin until they're a dizzying blur. Only this skater weighs more than our sun and is made of pure, crushing neutronium. But how does something so massive reach such insane speeds? It all comes down to the conservation of angular momentum. When a massive star collapses into a neutron star, its original rotation gets amplified dramatically, like an ice skater spinning faster as they pull in their arms, but scaled up to cosmic proportions. A star that might have rotated once every few weeks suddenly shrinks from millions of miles across to just 12 miles wide, compressing its spin into a frenetic, jaw-dropping pace. And because there's almost no friction in space to slow them down, pulsars can maintain these ridiculous speeds for millennia, their precision so flawless they rival atomic clocks in accuracy. What's even wilder is how we detect them. Pulsars emit beams of radiation, usually radio waves or X-rays, from their magnetic poles, and if those poles aren't perfectly aligned with their spin axis, the beams sweep across space like a cosmic searchlight. From Earth, we see these as rapid, clockwork pulses of light, sometimes flashing dozens or even hundreds of times per second. It's as if the universe installed a strobe light inside a neutron star and set it to hyperdrive. Some pulsars, like the famous Crab pulsar, even flicker in visible light, a tiny, relentless heartbeat in the wreckage of a supernova that exploded nearly 1,000 years ago. Yet for all their precision, pulsars aren't forever. Over millions of years, their powerful magnetic fields gradually sap their energy, slowing their spins like a weary top. But until then, they serve as some of nature's most fascinating timekeepers and laboratories. By studying the exact timing of their pulses, astronomers have confirmed Einstein's theory of general relativity, detected the faint ripples of gravitational waves, and even found planets orbiting these unlikely stellar survivors. They're not just cosmic oddities, they're tools that let us probe the very fabric of spacetime itself. If you could stand on the surface of a neutron star and survive the experience, you'd witness gravity turned up to 11. These cosmic monsters boast surface gravity 100 billion times stronger than Earth's, a force so intense it doesn't just pull, it warps the very fabric of reality. Picture this, the gravity is so crushing that if you dropped a marshmallow from just 1 meter above the surface, it would hit the ground at half the speed of light, releasing as much energy as a hydrogen bomb. That's not just strong gravity, it's gravity on steroids, bending the rules of physics until they snap. This unimaginable force does something even stranger to light. Normally, light travels in straight lines, but near a neutron star, spacetime itself is so distorted that photons curve like they're racing around a cosmic funhouse mirror. If you could hover nearby in some indestructible spacecraft, you'd see the star's far side stretched and warped, wrapping around the horizon like a twisted halo. Some neutron stars spin so fast that their gravity creates frame dragging, a phenomenon where they literally drag space-time around with them like a spoon swirling honey. Einstein predicted this effect, but neutron stars take it to extremes, twisting the universe's canvas into knots. And here's where it gets even weirder. The star's gravity is so intense that it acts like a lens, magnifying and distorting anything behind it. Imagine looking at a distant galaxy through this cosmic telescope, only instead of a clear image, you'd see multiple stretched copies of it, a ghostly echo created by light taking different paths around the star's gravitational well. It's like peering through a kaleidoscope forged by gravity itself. Even time isn't safe near these objects. Clock ticks slow to a crawl under such extreme gravity. An hour on the surface could mean years passing elsewhere in the universe. Yet for all their terrifying power, neutron stars are also cosmic gold mines for scientists. By studying how their gravity bends light, astronomers can test relativity in ways no Earth-bound lab ever could. Some neutron stars even have companion stars, and as they orbit, the warping of space-time around them sends out ripples, gravitational waves that we can detect here on Earth. These subtle tremors in the fabric of reality are like cosmic breadcrumbs, leading us closer to understanding how gravity works at its most extreme. So while we'll never set foot on a neutron star, their relentless gravity is doing us a favor. It's turning the universe into a classroom where physics gets pushed to its breaking point, and that's where the most exciting lessons are learned. Neutron stars already push the limits of what we consider extreme, but there's a special class of these cosmic beasts that make ordinary neutron stars look almost tame. Meet magnetars, the universe's ultimate electromagnets, with fields so strong they could strip the information from every credit card on Earth, from halfway across the galaxy. These rare stellar remnants possess magnetic fields measuring around 10 quadrillion times more powerful than our planets, a number so large it barely makes sense. To put that in perspective, if a magnetar floated as close as the Moon, its magnetic grip would be strong enough to rearrange the atoms in your body from 240,000 miles away. Your very molecules would start realigning, turning you into a cloud of scattered particles before you even knew what hit you. What creates such an incomprehensible force? When certain neutron stars form, their already intense magnetic fields get amplified to nightmarish levels during the supernova collapse. As the star's core implodes, its magnetic lines get twisted and concentrated, like taking all of Earth's magnetic field and cramming it into a space the size of a basketball. The result is a magnetic pressure cooker where physics starts behaving in bizarre ways. Electrons can't even maintain their usual orbits. The field warps their paths into needle-thin spirals. Atoms stretch into long, thin strings under the strain, a state of matter that exists nowhere else in nature. And if two magnetars ever collided, the resulting magnetic burst would outshine every star in our galaxy combined, briefly making it the brightest object in the observable universe. But here's where it gets practical in the scariest way. Magnetars don't just sit quietly, they erupt. In 2004, a magnetar 50,000 light-years away unleashed a gamma-ray flare so powerful it briefly ionized Earth's upper atmosphere, despite being halfway across the Milky Way. Had it been within 10 light-years, that blast could have stripped our ozone layer entirely. Even more unsettling are starquakes, when a magnetar's rigid crust cracks under magnetic stress, releasing energy equivalent to 100 trillion atomic bombs. The aftermath, a pulsating glow visible across interstellar space, like a cosmic distress signal written in X-rays. Yet for all their destructive potential, magnetars are gold mines for astrophysicists. Their extreme magnetic environments allow us to study quantum electrodynamics under conditions no lab could ever replicate. Some theories suggest their interiors might contain exotic matter like superconducting fluids or even free quarks, particles that normally only exist split apart inside atoms. And when magnetars occasionally glitch, suddenly speeding up their rotation, it gives us clues about the bizarre physics happening beneath their surfaces. So while we might not want one anywhere near our solar system, these terrifying objects are rewriting our understanding of how matter behaves when pushed to the absolute edge of possibility, proving once again that neutron stars aren't just dead stars, but some of the most dynamic laboratories in the cosmos. Among all the cosmic timekeepers, pulsars stand out as nature's most precise metronomes, beating with a regularity so flawless it puts even our most advanced atomic clocks to shame. These spinning neutron stars emit beams of radiation, usually radio waves, that sweep past Earth like clockwork, creating pulses so consistent their timing can be predicted down to microseconds over decades. The millisecond pulsar PSRB 1937 plus 21, for instance, spins 642 times per second with such stability that it would take 250 million years for its rhythm to drift by even a single second. That's like a wristwatch staying accurate to within a fraction of a second since the time dinosaurs walked the Earth, a level of precision that defies human engineering. What makes this even more astonishing is how we've harnessed these cosmic timekeepers. Back in 1974, astronomers included a pulsar map on the Voyager Golden Records, a celestial roadmap etched with the rhythms of 14 nearby pulsars. Each one was plotted by its unique pulse frequency, an interstellar Morse code that could, in theory, guide extraterrestrial explorers to Earth's location in the galaxy. Think of it as a cosmic GPS, where every pulsar acts like a lighthouse whose blinking pattern is so distinct it can't be mistaken for anything else. Even today, scientists are experimenting with using pulsar signals to navigate spacecraft autonomously beyond Earth's orbit, turning the heavens into a natural navigation network. But the real magic lies in what pulsars reveal about the universe itself. Because their pulses arrive with such predictable regularity, even the tiniest deviations can hint at unseen cosmic phenomena. When a pulsar's timing shifts slightly, it might mean it's being tugged by an orbiting planet, warped by gravitational waves, or even distorted by dark matter drifting through space. In 2017, astronomers used pulsar timing arrays to detect the faint background hum of gravitational waves, ripples in spacetime caused by colliding supermassive black holes. It's like listening to the universe's heartbeat and hearing the echoes of events billions of years old. Yet pulsars aren't just tools for exploration, they're also natural laboratories for testing physics at its limits. Their intense gravity slows time in ways predicted by Einstein, making them perfect for probing relativity. Some millisecond pulsars, spun up by stealing matter from companion stars, act like cosmic gyroscopes, their stable rotations helping scientists track subtle spacetime distortions. Others, like the double pulsar system PSRJ07 3039, orbit each other so precisely they've become the ultimate testbed for general relativity, confirming Einstein's predictions with unprecedented accuracy. So while we may never build a clock as precise as a pulsar, their relentless ticking does something far more valuable. It turns the universe into a grand experiment, one where every pulse is a clue waiting to be decoded. Whether guiding spacecraft, unmasking hidden planets, or eavesdropping on black hole collisions, these celestial timekeepers remind us that sometimes the most profound discoveries come from simply listening to the rhythm of the stars. Deep in the cosmos, two neutron stars circle each other in a deadly dance, spiraling closer with each orbit until, in a fraction of a second, they collide. The result, a cosmic alchemy so powerful it forges the heaviest elements in the universe, scattering gold, platinum, and other precious metals across space like glitter from an explosion. This isn't science fiction, it's the spectacular process behind where your wedding ring or smartphone circuitry ultimately came from. The breakthrough moment came in August 2017, when astronomers witnessed this phenomenon firsthand. For the first time in history, they detected both gravitational waves, ripples in spacetime, and a burst of light from the same event, a neutron star merger roughly 130 million light-years away. The gravitational wave observatories LIGO and Virgo caught the initial signal, a faint chirp lasting about 100 seconds as the stars spiraled inward. Then, just under 2 seconds later, telescopes across the globe spotted a gamma-ray burst, followed by a glowing afterbirth called a kilonova. This wasn't just light, it was the radioactive glow of newly minted elements forming in real time. Here's how the magic happens. When neutron stars merge, the extreme conditions, temperatures reaching trillions of degrees and densities surpassing atomic nuclei, trigger rapid neutron capture, or the R process. Free neutrons bombard atomic seeds, building them up into heavier elements faster than they can decay. In moments, the collision spews out material rich in gold, platinum, uranium, and other rare metals, with a single merger producing enough gold to outweigh Earth several times over. That kilonova in 2017, astronomers estimate it created around 200 Earth masses of solid gold alone, along with a cosmic cocktail of other heavy elements. Before this discovery, scientists debated where these heavy elements originated. Supernovae were candidates, but their explosions couldn't fully explain the abundance of gold and platinum in the universe. Kilonovas solved the mystery, proving that neutron star collisions are the universe's ultimate jewelry stores. Even more astonishing, the debris from these mergers gets incorporated into new stars, planets, and eventually life itself. The gold in your ring likely spent billions of years traveling through space, forged in a cataclysm so violent it warped spacetime before finding its way into Earth's crust. But the implications go beyond bling. That 2017 event marked the dawn of multi-messenger astronomy, where scientists combined gravitational wave data with traditional telescope observations to study one event across multiple wavelengths. It confirmed Einstein's prediction that gravitational waves travel at the speed of light and provided the most precise measurement yet of the universe's expansion rate. This collision didn't just create precious metals, it minted a new way to explore the cosmos, proving that sometimes the universe's most violent encounters hold the keys to its deepest secrets. So the next time you hold something made of gold, remember, you're touching stardust with a backstory wilder than any treasure hunt, a relic from a time when two dead stars collided in the darkness, scattering their glitter across the galaxies. At the moment of their birth, neutron stars are the hottest known objects in the universe, so hot that the numbers barely make sense. For a brief, searing instant after a supernova explosion, a newborn neutron star's surface blazes at around 1 million degrees Celsius, while its core rockets past 10 million degrees. That's hotter than the sun's core, which simmers at a comparatively mild 15 million degrees. But unlike the sun, which has been steadily burning for billions of years, a neutron star achieves these staggering temperatures in mere seconds. A flash of heat so intense it could vaporize an entire solar system's worth of material in the blink of an eye. What makes this heat even more mind-bending is how it's generated. While the sun relies on nuclear fusion, slowly converting hydrogen into helium, a neutron star's heat comes from sheer gravitational collapse. Imagine taking all the energy our sun will produce over its entire 10 billion-year lifespan and releasing it all at once. That's roughly the energy packed into the birth of a single neutron star. And because these objects are so dense, with almost no empty space between particles, that heat can't escape easily. It's like trying to cool a white-hot cannonball by wrapping it in a mile-thick blanket of steel. Yet even these cosmic furnaces can't stay scorching forever. Over time, neutron stars cool, but not in any way we'd recognize. For the first few years, they shed heat primarily by emitting neutrinos, ghostly particles that stream straight through solid matter. A single teaspoon of neutron star material would release so many neutrinos that they'd outnumber all the grains of sand on Earth. After about 10,000 years, photons, light particles, take over as the dominant cooling mechanism, and the star's surface gradually dims from blue-white to red. But here's the catch: even after a million years, when their surface has cooled to a mere few 100,000 degrees, their cores remain blistering. Trapped by the star's insane density, that residual heat lingers like an ember in a cosmic furnace, slowly fading over billions of years. This cooling process isn't just a curiosity, it's a window into the neutron star's hidden interior. By studying how quickly different stars cool, astronomers can infer what's happening deep inside them. Some neutron stars cool faster than expected, hinting at exotic states of matter like superfluids, where neutrons flow without friction like liquid helium on a cosmic scale. Others cool unevenly, suggesting their magnetic fields are funneling heat in bizarre, asymmetrical patterns. Each temperature drop is a clue, helping scientists piece together the puzzle of what happens to matter when it's crushed beyond recognition. So while neutron stars may start as the universe's hottest objects, their slow fade into darkness is just as fascinating. They're not just cooling corpses, they're cosmic clocks, their temperatures ticking down like a stellar countdown. And with every degree they lose, they whisper secrets about the fundamental nature of matter, gravity, and time itself, proving that even in their dying embers, neutron stars still blaze with scientific wonder. Even neutron stars, with their unimaginable density, aren't indestructible. Their crusts can fracture under pressure, triggering seismic events so violent they'd make Earth's earthquakes look like gentle ripples in a pond. These starquakes occur when a neutron star's rigid outer layer, a lattice of atomic nuclei packed tighter than sardines, suddenly cracks under the strain of its own rotation or magnetic field. The result, a cosmic tremor that unleashes more energy in a millisecond than our sun emits in 100,000 years. Picture snapping a giant rubber band wrapped around a bowling ball. Except the bowling ball is 12 miles wide, spins faster than a jet turbine, and the snap releases enough X-rays to sterilize a small galaxy. The most dramatic starquakes happen on magnetars, where magnetic fields are so intense they literally twist the star's crust like taffy. When these crustal plates finally give way, the rebound vibrates through the star, sending out gamma-ray flares detectable across intergalactic distances. In 2004, a magnetar named SGR 1008-10620 produced a starquake so powerful its flash briefly outshone the full moon, despite being 50,000 light-years away. For a tenth of a second, it was the brightest object ever recorded outside our solar system, emitting more energy than the sun does in 150,000 years. If that quake had occurred within 10 light-years of Earth, it could have triggered a mass extinction by stripping our atmosphere's ozone layer. But here's the twist: these cataclysms aren't just destructive, they're cosmic Rosetta Stones for understanding neutron star interiors. When a starquake rattles a magnetar, it rings like a bell, oscillating at precise frequencies that reveal what's hidden beneath the surface. By studying these vibrations, astronomers have deduced that neutron star crusts are likely a bizarre mix of crystalline metals and free-flowing neutrons, with a mantle of superfluid particles beneath. Some starquakes even produce aftershocks that follow mathematical patterns eerily similar to earthquakes, suggesting universal physics might govern both celestial and terrestrial tremors. The aftermath of a starquake is just as fascinating. The cracked crust oozes a torrent of charged particles, fueling X-ray outbursts that can last for years. In 2007, magnetar Cs UJ 164,710 to 455,216 emitted a burst so persistent it brightened by 100 times in X-ray observations, like a cosmic wound slowly healing. These lingering glows act as forensic evidence, helping scientists map the star's magnetic anatomy. Some researchers even speculate that starquakes could explain fast radio bursts, those mysterious, millisecond-long radio signals from distant galaxies, if the quake's shockwaves interact with surrounding plasma in just the right way. So while starquakes might sound like astrophysical curiosities, they're actually VIP passes to the neutron star's secret inner workings. Every crustal crack, every gamma-ray scream, carries encoded details about densities, magnetic fields, and states of matter we can't replicate on Earth. They remind us that even in death, stars refuse to go quietly, preferring to shatter the silence with eruptions that light up the cosmos, and in doing so, illuminate the darkest corners of physics. Imagine a world where the sky is lit not by a gentle sun, but by the strobe-like flashes of a pulsar, a neutron star spinning so fast it blinks like a cosmic disco ball. These aren't the stuff of science fiction, they're real planets orbiting some of the most hostile environments in the universe. In 1992, astronomers made a jaw-dropping discovery. The first confirmed exoplanets weren't circling a normal star at all. They were orbiting a pulsar named PSRB 1257+12, a stellar corpse spinning over 6,000 times per minute, its radiation blasting space with deadly intensity. Yet somehow, against all odds, 3 rocky worlds clung to existence in this apocalyptic environment. How does anything survive the birth of a neutron star? The parent star's supernova explosion should have vaporized any nearby planets, or at least flung them into deep space. One theory suggests these pulsar planets might be second-generation worlds, formed from the debris of the explosion itself. As the supernova's shockwave plowed through surrounding material, it could have compressed gas and dust into a new disk, a celestial phoenix rising from the ashes. From this disk, fresh planets coalesced, this time under the pulsar's eerie glow. Another possibility: these worlds were once gas giants, their outer layers stripped away by the neutron star's radiation, leaving behind dense, rocky cores, cosmic survivors hardened in the furnace of catastrophe. Life on these planets would be, unlikely to say the least, bathed in lethal X-rays and gamma rays. Their surfaces would be bombarded by particle winds moving near light speed. The day-night cycle would be surreal, lit by a pulsar's razor-thin beam slicing across the sky like a cosmic scythe. And yet, there's a haunting beauty to the idea. Worlds that somehow endured the universe's most violent rebirth, orbiting a tombstone of the star that birthed them. The real surprise: pulsar planets might not be rare. Another system, PSRB 1600-2026, hosts a gas giant that's over 12 billion years old, twice the age of Earth, and possibly the oldest known planet in the galaxy. It's a fossil from the universe's youth, orbiting a stellar relic in a quiet corner of a globular cluster. These discoveries force us to rethink where and under what conditions planets can form. If worlds can exist around dead stars, then planetary systems might be far more resilient and far more creative than we ever imagined. So while pulsar planets will never be vacation destinations, they're cosmic proof that even in destruction, the universe finds ways to rebuild, spinning new worlds from the wreckage of the old and writing survival stories where we least expect them. Even the most precise cosmic clocks sometimes stutter. And when a neutron star suddenly speeds up its spin without warning, astronomers call it a glitch. Picture a spinning ice skater who, without pulling in their arms, inexplicably whirls faster for no apparent reason. That's exactly what happens with pulsars, these hyper-accurate timekeepers occasionally, and violently jump in rotation speed by a fraction of a second, as if the universe itself hit a cosmic fast-forward button. The Vela pulsar, one of the most active glitches, has sped up over 15 times since monitoring began, with one event in 2016 altering its spin by a staggering 1 part in a million, equivalent to Earth's day shrinking by 5 seconds overnight. So what's jolting these ultra-dense objects into sudden overdrive? The leading theory points to their mysterious interiors. Beneath a neutron star's solid crust, a crystalline layer harder than diamond, lies a neutron superfluid, a bizarre state of matter where particles flow without friction, like liquid helium cranked to cosmic extremes. Normally, this superfluid rotates in sync with the crust, but as the star's spin gradually slows due to magnetic braking, the superfluid can lag behind, storing angular momentum like a coiled spring. When the crust and superfluid suddenly recouple, perhaps due to microscopic cracks or shifts in the star's magnetic field, that pent-up energy transfers outward in a burst, kicking the star's rotation into overdrive. It's like a stalled engine abruptly catching, lurching the entire system forward. But glitches aren't just about speed, they're cosmic diagnostics. The the way a pulsar recovers from a glitch, sometimes overshooting, sometimes stabilizing, reveals secrets about its internal layers. Some neutron stars exhibit delayed glitches, where the speed-up happens in stages, suggesting multiple superfluid layers decoupling and recoupling at different depths. Others show permanent changes, hinting at crustal fractures or even vortices, tiny tornadoes of neutrons breaking free and surging toward the surface. The 2019 glitch of pulsar J0980843913 was so extreme it released energy equivalent to 1 billion atomic bombs, yet the star returned to normal within weeks, as if shrugging off the universe's most violent hiccup. The weirdest part, glitches might not be the only anomalies. A handful of neutron stars have exhibited anti-glitches, sudden slowdowns that defy explanation. Magnetar 1E 2259 plus 586, for instance, once slowed its spin by 2 millionths of a second in 2012, an event so perplexing it's still debated. Some theorists speculate these reversals could involve magnetic avalanches inside the star, where shifting field lines literally drag the crust backward, or pockets of exotic matter like quark soup bubbling up from the core. What's clear is that every glitch is a telegram from a neutron star's shadowy interior, a place where matter exists in states no laboratory can replicate. By cataloging these cosmic stutters, astronomers are piecing together a map of the impossible, a realm where gravity twists the rules, and a teaspoon of material holds the key to physics we've yet to dream up. On a neutron star, even a pebble would be a mountain, literally. These ultra-dense objects are so perfectly smooth that their surface irregularities max out at just a few centimeters tall. Yet under their crushing gravity, these minuscule bumps qualify as the steepest topographic features in the known universe. Imagine Mount Everest squeezed down to the height of a soda can but weighing 1 billion times more. That's what passes for a mountain on a neutron star, where gravity 100 billion times stronger than Earth's flattens everything into near-perfect smoothness, leaving only the most stubborn atomic scale imperfections to jut out like cosmic speed bumps. What creates these bizarre mountains? It's all about balance, or more accurately, imbalance. A neutron star's crust, a lattice of atomic nuclei packed tighter than bullets in a rifle barrel, isn't perfectly uniform. Tiny density variations or the strain of a ludicrously powerful magnetic field can warp the crust ever so slightly, producing high spots no thicker than a pencil. But here's the catch: because the star's gravity is so intense, even these centimeter-high bumps exert unbelievable pressure on the space-time beneath them. A single neutron star mountain weighing more than the entire Himalayas could fit comfortably in your living room, if your living room could survive the gravitational tidal forces that come with it. These distortions aren't just curiosities, they might be detectable across interstellar space. When a neutron star spins, its mountains whip through space-time like spoons stirring honey, creating ripples in the fabric of reality itself. Gravitational wave observatories like LIGO and Virgo are hunting for these faint tremors, which should carry the distinct fingerprint of a rotating neutron star's topography. The challenge: the signals are vanishingly weak. A typical neutron star's gravitational waves would carry less power than a light bulb, but after traveling thousands of light years, even that whisper could reveal the star's hidden contours. Some theories suggest the largest mountains might form where the star's magnetic field punches through the crust, creating magnetic bruises that resist being smoothed away. Others propose that collisions between neutron stars could leave behind temporary bulges as the merged object settles into its new shape. Regardless of their origin, these mountains are more than just cosmic trivia. They're stress tests for the limits of material strength. Under normal circumstances, a neutron star's crust should be strong enough to support mountains dozens of centimeters tall, but observations suggest most stay under 5 centimeters. That discrepancy hints at something extraordinary. The crust might be cracking under the strain, triggering tiny starquakes that constantly sand down these gravitational speed bumps. So while we'll never hike these mountains, their existence and their limits teach us how matter behaves when pushed to the edge of physics. Every bump, every ripple, is a clue written in gravity's own language, waiting to be decoded by the next generation of telescopes and wave detectors. In the end, neutron star mountains prove that even in perfection, the universe leaves room for imperfections, and those imperfections might just help us hear the stars themselves. The sheer compactness of a neutron star defies all earthly intuition. Here's an object with twice the mass of our Sun, crushed into a sphere no wider than Manhattan. Picture all that cosmic bulk squeezed into a space so small you could drive across it in 20 minutes. If our Sun were suddenly compressed to neutron star density, it would shrink from 865,000 miles across to just 12 miles smaller than London's orbital motorway. Yet this tiny package contains enough matter to outshine most stars in the galaxy, proving that in the universe's extremes, size and power have no correlation. What makes this compression even more staggering is how it warps our understanding of matter. Under normal conditions, atoms are mostly empty space. If a hydrogen atom were blown up to the size of a football stadium, its nucleus would be a mere pea at the 50-yard line. But in a neutron star, gravity obliterates that emptiness. Electrons get slammed into protons, converting them into neutrons until the entire star becomes one giant atomic nucleus, a seething ocean of nuclear particles with no breathing room. It's like taking every car, building, and person on Earth and compressing them into a single sugar cube, except here, the ingredients are the remains of a stellar giant. But don't let their modest dimensions fool you. A neutron star's gravitational pull at its surface is 100 billion times stronger than Earth's. If you somehow hovered just a meter above one, you'd accelerate toward it at over half the speed of light by the time you hit the surface. That's not falling, that's being fired from a cosmic cannon. Even light struggles to escape. Photons leaving the surface lose so much energy climbing out of the gravity, well, that visible light shifts to X-rays by the time it reaches distant observers. The crazy part, some neutron stars are even smaller. The record holder, Pulsar J0453 plus 1559, might be just 12 miles wide, so dense that if you scooped a teaspoon of its material, it would weigh as much as 5 billion elephants. Yet it spins 15 times per second, whipping its entire mass around faster than a Formula One engine revs. This paradox, unimaginable mass packed into laughably tiny volumes, is what makes neutron stars the universe's ultimate magic trick. Cosmic matter folded into itself until the very laws of physics start to fray at the edges. And here's the kicker: despite their minuscule size, neutron stars can influence worlds light years away. Their magnetic fields, trillions of times stronger than Earth's, carve out magnetospheres so vast they could engulf entire solar systems. A pulsar's beam might be narrow, but its energetic reach stretches halfway across the galaxy. So while these objects might fit inside a city's skyline, their cosmic footprint is anything but small, proof that in space, the tiniest things often cast the longest shadows. While radio pulsars might be the most famous, some neutron stars broadcast their presence in far more energetic languages, blasting out X-rays and gamma rays with enough punch to outshine entire galaxies in these wavelengths. Take the Crab pulsar, the spinning heart of the supernova witnessed in 1054. This cosmic powerhouse doesn't just flicker in radio waves, it screams in X-rays and gamma rays, flashing 30 times per second like a hyperactive strobe light. The energy behind these pulses is staggering. A single beam from the Crab contains more power than all the electricity humanity generates in a year, packed into a burst shorter than the blink of an eye. What fuels these high-energy fireworks? The answer lies in the extreme physics around neutron stars. Unlike radio pulsars, which emit from their magnetic poles, X-ray and gamma-ray pulsars often derive their energy from external sources. Some, like the crab, are rotation-powered. Their beams come from charged particles accelerated to near light speed by the star's spinning magnetic field. These particles spiral along magnetic lines, crashing into the surrounding nebula and releasing X-rays in violent collisions. Others, called accretion-powered pulsars, steal matter from companion stars, funneling gas onto their surfaces in swirling disks. When this superheated plasma slams into the neutron star's magnetic poles, it ignites X-ray bursts so bright they temporarily outshine every other X-ray source in the sky. Then there are the real outliers, magnetars. These neutron stars with magnetic fields 1,000 times stronger than typical pulsars occasionally unleash gamma-ray flares, sudden, apocalyptic explosions of energy detectable across the universe. In 2004, a magnetar 50,000 light-years away released a gamma-ray burst so intense it momentarily ionized Earth's upper atmosphere. Had it been within 10 light-years, it could have triggered a mass extinction. These eruptions likely come from magnetic reconnection, where twisted field lines snap like overstretched rubber bands, releasing pent-up energy in a catastrophic cosmic short-circuit. Yet even these monsters aren't the most extreme. Some neutron stars, like Geminga, are radio-quiet but shine brilliantly in gamma rays alone. Their beams might originate from polar caps so hot they glow in high-energy light, or from particle jets screaming outward along the star's rotation axis. Others, like Pulsar J 2030 plus 4415, drag entire clouds of interstellar material behind them, creating gamma-ray wakes as they plow through space at hundreds of kilometers per second. The takeaway: neutron stars are multilingual. Each variety speaks in a different wavelength, telling its own story of gravity, magnetism, and cosmic violence. Whether whispering in radio waves or shrieking in gamma rays, they remind us that the universe's most compact objects are also some of its loudest. In the cosmic dance of binary systems, some neutron stars turn into outright thieves, slowly devouring their stellar companions bite by bite. These celestial vampires don't need fangs. Their weapon is gravity itself, so intense it can rip gas straight off a nearby star and funnel it into a glowing, swirling death spiral. The result: an accretion disk, a superheated carousel of plasma orbiting the neutron star at nearly the speed of light, where temperatures rocket to millions of degrees and magnetic fields twist the chaos into violent outbursts visible across the galaxy. Take X-ray binaries, some of the most luminous objects in the universe. In these systems, a neutron star partners with a living star, often a red giant or supergiant close enough to steal its outer layers. As material gets pulled away, it spirals inward, accelerating to relativistic speeds and heating up until it emits X-rays with such intensity that a single system like Scorpius X1 can outshine the entire rest of the Milky Way in X-ray light. The process isn't gentle. When gas crashes onto the neutron star's surface, it triggers thermonuclear explosions called Type I X-ray bursts, flares so powerful they release more energy in seconds than our sun does in weeks. But the real drama unfolds when the stolen material overflows. Some neutron stars, like the famed Hercules X1, have magnetic fields strong enough to channel incoming plasma into columns that slam onto their poles like cosmic fire hoses. These accretion columns glow with such ferocity they create pulsating X-ray beams, turning the neutron star into a high-energy lighthouse. Other systems, like Circinus X1, produce jets, narrow streams of particles shot outward at nearly light speed, carving through space like celestial blowtorches. The most extreme cases: transient X-ray binaries, where the neutron star gorges on material until the disk becomes unstable, leading to eruptions that briefly make it the brightest X-ray source in the galaxy. In 2009, the system XTJ 1550-564 erupted so violently it was visible to amateur telescopes despite being 20,000 light-years away. And when the meal ends, the neutron star often leaves its companion star battered and shrunken, a stellar corpse orbiting the very object that doomed it. Yet this cosmic cannibalism has a silver lining. It's teaching us how matter behaves under extreme conditions. By studying these X-ray symphonies, astronomers have mapped magnetic fields, measured spin rates, and even glimpsed the event horizons of black holes in similar systems. Every stolen atom, every burst of radiation is a clue, a piece of the puzzle showing how the universe's most violent relationships can illuminate its deepest secrets. Even among the universe's most extreme objects, some neutron stars manage to feel almost familiar. Take RxJ 1856, 5-3754, the closest known neutron star to Earth, drifting through space just 400 light-years away in the constellation Corona Australis. That might sound distant, but in cosmic terms, it's practically next door. If the Milky Way were mapped onto the scale of a football field, this stellar remnant would be orbiting just a few inches from Earth's position. Discovered in 1992, this dim cosmic ember initially fooled astronomers. Its faint X-ray glow suggested something much farther away, until precise measurements revealed its true distance and its extraordinary nature. Though it emits barely any visible light, RxJ 1856, 5-3754 glows in X-rays and ultraviolet, the last whispers of heat from a surface still simmering at around 700,000 degrees Celsius. That makes it one of the few neutron stars we've imaged directly, its X-ray portrait showing a tiny, perfect sphere no larger than a small asteroid. What makes this neutron star especially intriguing is what it lacks. Unlike pulsars, it doesn't beam radio waves or spin frenetically. Unlike magnetars, it doesn't erupt in violent flares. It's quiet, almost serene. Astronomers call it a radio-quiet isolated neutron star, a cosmic retiree cooling gently after the chaos of its birth. Its calm demeanor suggests it never had a binary companion to steal from, nor a strong magnetic field to stir up trouble, just a solitary voyage through the galactic neighborhood. Yet RxJ 1856, 5-3754 still harbors mysteries. Its X-ray spectrum hints at an atmosphere, possibly a thin layer of carbon or oxygen clinging to the surface against the star's crushing gravity. Some theories suggest the star's light might even be polarized, twisted by its magnetic field into a subtle cosmic fingerprint. And in 2002, astronomers spotted a faint optical counterpart, a dim blue pinpoint that might be light bent and focused by the star's gravity like a lens. So while it may not be flashy, this quiet neighbor offers something rare, a neutron star stripped of extremes, letting us study the basics of these bizarre objects without the distractions of beams, bursts, or companions. It's a reminder that even the universe's most violent creations can, given enough time, settle into something approaching cosmic tranquility. Deep inside a neutron star where pressures dwarf anything in our solar system, matter might not just be compressed, it could be utterly transformed. Beneath the crushing weight of 1 trillion Earth atmospheres, particles we consider fundamental might dissolve into something even more exotic, a swirling soup of free quarks and gluons known as quark-gluon plasma. This state of matter hasn't existed naturally since the universe's first microseconds after the Big Bang, except, perhaps, in the cores of neutron stars, where conditions recreate that primordial chaos every second. The numbers involved are mind-numbing. At around 2 to 3 times the density of an atomic nucleus, the very structure of neutrons themselves could break apart. Protons and neutrons, normally made of 3 bound quarks, might melt into a sea where quarks flow freely, unconfined by the usual rules. Some theories suggest this quark matter could evolve further, with up and down quarks converting into strange quarks, a heavier, more unstable variety creating strange matter, so stable it could theoretically persist outside the star. That last possibility isn't just intriguing, it's borderline apocalyptic. If strange matter is truly stable, a single droplet escaping a neutron star could, upon contact with normal matter, trigger a runaway conversion process. Picture a cosmic domino effect where planets, stars, even entire galaxies could be transmuted into lumps of this hyper-dense alien substance, the scariest part. We might already have evidence. In 2018, the neutron star merger observed by LIGO produced a remnant heavier than expected, one that collapsed into a black hole slower than models predicted. Some scientists speculate this delay could mean the merged object briefly formed a quark core, its exotic matter resisting collapse just a fraction longer. Other clues come from massive neutron stars like Pulsar J07, 40 plus 6620, which weighs in at over 2 solar masses yet shows no signs of quark softening. Its resilience hints that quark matter, if it exists, might only emerge at densities even higher than we've observed. Yet for all the theories, the truth remains locked inside these cosmic vaults. Laboratories like CERN can create quark-gluon plasma in particle collisions, but those flashes last mere fractions of a second. Neutron stars, by contrast, are nature's pressure cookers, running sustained experiments we can't yet replicate. Every unusual glitch, every gravitational wave signature, might be a breadcrumb leading us closer to understanding whether the universe's ultimate density harbors matter unlike anything we've ever seen, or whether it's waiting quietly to rewrite reality itself. Even the fastest pulsars can't keep up their dizzying spins forever. Over eons, these cosmic lighthouses gradually lose energy, their furious rotations slowing until their once bright beams fade into silence. This slow cosmic wind down happens because pulsars aren't just spinning in a vacuum. They're dragging their immense magnetic fields through space, and that resistance acts like an interstellar brake. Every rotation releases electromagnetic radiation that carries away energy, causing the star to lose speed by fractions of a second each year. The Vela pulsar, for instance, was clocked spinning 11 times per second when discovered in 1968. Today, it's down to about 10 rotations, a small change, but over millennia, that slowdown adds up. For young, energetic pulsars, the deceleration is barely noticeable, but older ones like Pulsar J 2144, 3933 have slowed to a leisurely 1 rotation every 8 seconds, their beams now too weak to detect from Earth. The rate isn't constant either. Glitches can temporarily speed them up, while magnetic field decay or gravitational wave emission might accelerate their decline. Astronomers call the point when a pulsar's spin becomes too slow to power its beams the death line, a theoretical threshold where the star's rotation can no longer sustain the particle acceleration needed to produce detectable radio waves. This typically happens when a pulsar's period stretches beyond several seconds, though the exact timing depends on its magnetic field strength. Some pulsars cross this line quietly, their beams winking out like a dying light bulb. Others might experience death throes with sporadic, weaker bursts before falling silent entirely. But here's the twist: even after crossing the death line, neutron stars aren't truly dead. They simply become invisible to our telescopes, continuing to cool and spin down over billions of years. Some might later reawaken if they accrete material from a companion star, spinning back up to become X-ray pulsars. Others could collide with another neutron star, triggering a spectacular rebirth as a kilonova. The universe rarely lets anything go quietly, even in death. A pulsar's story isn't truly over, just waiting for the right conditions to write its next chapter. So while we might never again hear the rhythmic pulses of these aged stars, their legacy lives on in the gravitational waves they emit, the heavy elements they've scattered, and the mysteries they leave behind, silent memorials to the universe's most precise clocks. Some neutron stars don't just steal matter, they fire it back into space at nearly the speed of light, creating jets so powerful they rival those of supermassive black holes. These aren't gentle streams, they're particle accelerators stretching light years into the cosmos, twisting space-time as they go. Take SS433, one of the most bizarre systems ever discovered. Here, a neutron star orbits a supergiant companion, siphoning off gas so furiously that it launches twin jets at over a quarter the speed of light, but with a cosmic quirk. The jets wobble like a spinning top, carving out a corkscrew-shaped trail across interstellar space. What makes these jets so extraordinary is how they mirror, and sometimes outshine, their larger black hole cousins. While quasars and active galactic nuclei blast jets millions of light-years long, neutron star jets operate on a smaller but no less violent scale. In systems like Circinus X1 or Scorpius X1, jets punch through surrounding gas clouds, heating them to X-ray, emitting temperatures and creating shock waves visible across the electromagnetic spectrum. The energy packed into these beams is mind-bending. A single jet from a neutron star like her X1 carries enough power to supply Earth's energy needs for trillions of years. The physics behind these jets is even more fascinating. As material spirals toward the neutron star in an accretion disk, magnetic fields channel some of it outward along the rotation axis, launching twin beams of plasma. But unlike black holes, where jets originate near the event horizon, neutron star jets likely form much closer to the surface, where the star's fierce magnetic field whips particles into a frenzy before slingshotting them into space. Some jets, like those in SS433, also precess, meaning their orientation slowly rotates over time. This creates a helical pattern in the surrounding nebula, like a cosmic sprinkler watering the galaxy with high-energy particles. The real showstopper, these jets aren't just pretty light shows their particle physics labs. In systems like PSRB 1259-63, jets collide with interstellar gas, creating gamma-ray flares that help scientists study how particles behave at relativistic speeds. Others, like the microquasar GRS1915+105, exhibit jet speeds that appear faster than light, an illusion caused by their narrow angle toward Earth, but no less spectacular. So while black holes might steal the spotlight, neutron stars prove you don't need infinite density to power some of the universe's most dazzling ejections. Whether wobbling like a drunk lighthouse or punching through nebulae at nearly light speed, these miniature jets remind us that even the smallest cosmic objects can leave the biggest marks. Neutron stars aren't just cosmic oddities, they're nature's ultimate testing grounds for Einstein's theory of general relativity. Take the Hulse-Taylor binary pulsar discovered in 1974. This pair of neutron stars, locked in a gravitational waltz, provided the first indirect proof of gravitational waves decades before LIGO made direct detections. Every 8 hours, these ultra-dense objects swing around each other at nearly 1% the speed of light, warping space-time so severely that their orbit shrinks by about 3.5 meters per year, precisely matching Einstein's calculations of energy lost to ripples in the fabric of reality. What makes this system so special? It's a perfect storm of extreme physics. The pulsar's clock-like radio pulses serve as precision tracking beacons, allowing astronomers to map its orbital dance with sub-millisecond accuracy. As the stars spiral inward, their gravitational pull distorts time itself. Clocks on one star tick slower when nearer its massive companion, just as relativity predicts. Even subtle effects like geodetic precession, where a spinning object's axis wobbles in curved space-time, are observable here, with the pulsar's spin axis shifting by 4.2 degrees per year like a cosmic gyroscope gone slightly off-kilter. But the real triumph came in 1993 when Russell Hulse and Joseph Taylor won the Nobel Prize for proving this orbital decay matched Einstein's predictions within 0.2%, a triumph of theoretical foresight meeting cosmic verification. Their work didn't just confirm gravitational waves existed, it showed neutron stars could serve as laboratories where space-time itself becomes the experiment. Modern discoveries have taken this even further. The double pulsar system Pulsar J0737 3039 two neutron stars where both beam radio waves at Earth has tested relativity to within 0.005% precision. Its orbit's gradual shrinking, frame-dragging effects, and even how its gravity bends the distant pulsar's radio signals all align flawlessly with Einstein's equations. Yet some theories suggest neutron stars might one day reveal where relativity breaks down, perhaps in their unimaginably dense cores, where quantum gravity effects could lurk. So while we celebrate Einstein's victories, these cosmic sentinels keep pushing the boundaries. Every pulse, every orbital shift is a challenge, asking whether our grasp of gravity holds true under the most extreme conditions the universe can muster. Some neutron stars don't just push the boundaries of physics, they act as time machines, beaming light from an era when the universe was barely out of its cosmic cradle. In 2022, astronomers detected a pulsar nearly 12 billion light-years away, its rhythmic pulses originating from a time when the cosmos was just 1.4 billion years old. Think about that. This stellar relic has been spinning uninterrupted since before Earth existed, before the Milky Way took its current shape, before most stars we see today were even born. Its light is a snapshot of the universe's rebellious teenage years, carrying secrets about how galaxies formed and space itself evolved during those chaotic early epochs. What makes these distant neutron stars so invaluable is how they illuminate the cosmic dark ages, the poorly understood period between the Big Bang's afterglow fading and the first stars flickering to life. Unlike quasars or supernovae, whose brilliance can obscure details, neutron stars emit cleaner, more predictable signals. Their precise pulses serve as backlights, allowing scientists to study the sparse intergalactic gas that absorbed parts of their radiation along the way. It's like using a strobe light to map fog. Every flicker reveals something new about the space it traveled through, but detecting these ancient beacons isn't easy. By the time their signals reach us, they're incredibly faint, often drowned out by closer, brighter objects. The record holder, Pulsar J0318+0253, was only spotted because its pulses arrived in a distinctive pattern that machine learning algorithms could pick out from radio telescope noise. Its discovery shattered expectations, proving that neutron stars formed far earlier in cosmic history than models predicted. Some may have been among the very first compact objects to emerge after the primordial stars died, their supernovae seeding the universe with heavy elements essential for planets and life. The real treasure lies in what their light encodes. As these signals traverse expanding space, their wavelengths stretch, subtly shifting based on the universe's expansion rate at different eras. By comparing ancient neutron stars' pulses with local ones, astronomers can measure how the cosmos has accelerated over billions of years, refining our understanding of dark energy's grip on spacetime. Others, like the distant magnetar Joby 215A, have revealed that the early universe's magnetic fields were surprisingly strong, hinting at turbulence in the infant cosmos that might have shaped galaxy formation. So while these time-traveling pulsars might seem like mere curiosities, they're actually rewriting cosmic history. Every pulse from the void is a message in a bottle, cast across eons, telling us how the universe grew up and how neutron stars, against all odds, became its most enduring storytellers. The crust of a neutron star isn't just hard, it's the strongest material in the known universe, a lattice of atomic nuclei packed so tightly it makes diamond look like tissue paper. Picture steel, then imagine something 10 billion times stronger. That's what neutron star crusts are made of. At these densities, atomic nuclei get squeezed into bizarre shapes, long, spaghetti-like strands or flat lasagna sheets, all tangled in a quantum mechanical web physicists call nuclear pasta. This isn't just theoretical, it's matter so dense a single cubic centimeter could outweigh every skyscraper on Earth combined. What makes this crust so indestructible? It's all about gravity's ruthless efficiency. Under pressures 1 trillion times Earth's surface, electrons get crushed into protons, turning them into neutrons. These neutrons then crystallize into a rigid matrix with atomic nuclei arranged in a pattern so tight it defies ordinary physics. The bonds between these particles are so strong they could withstand stresses that would vaporize any terrestrial material. Yet even this cosmic armor has its limits. When a neutron star's rotation slows or its magnetic field shifts, the crust can fracture, triggering starquakes that release more energy than 1 billion atomic bombs. The aftermath of these fractures is where things get truly surreal. Unlike Earth's crust, which breaks along fault lines, a neutron star's crust shatters in a way that sends vibrations rippling through the star's interior. These quakes can momentarily speed up the star's spin like an ice skater pulling in their arms during a stumble, creating the mysterious glitches astronomers observe. Some starquakes even emit bursts of X-rays or gamma rays, as if the star itself is screaming into the void. The 1999 starquake on magnetar SGR 1900+14, for instance, released a gamma-ray flare so powerful it temporarily disabled satellites and lit up Earth's upper atmosphere like a cosmic flashbulb. But here's the twist: these crusts might not be uniformly strong. Some regions, warped by unimaginable magnetic fields, could develop weak spots, cosmic fault lines where stress concentrates until the inevitable snap. Others might harbor mountains, tiny imperfections just centimeters high yet massive enough to distort spacetime itself. When these imperfections shift, they could generate gravitational waves, faint ripples in the fabric of reality that observatories like LIGO are now hunting. So while we'll never mine a neutron star's crust, its existence teaches us how matter behaves under conditions no lab could ever replicate. Every fracture, every tremor is a clue, a message from a realm where the ordinary rules of physics break down and strength gets redefined on a cosmic scale. Some neutron stars don't just orbit companion stars, they slowly cook them alive in a deadly cosmic embrace. Meet the Black Widow pulsars, named after the spider that devours its mate. These ruthless stellar remnants blast their partners with enough radiation to strip them away atom by atom. Picture a stellar vampire, but instead of fangs, it wields particle beams and gamma rays, a lighthouse of death spinning in the darkness, methodically dissolving the very star that keeps it company. The process is as brutal as it sounds. In these binary systems, the pulsar's intense magnetic field and rapid rotation accelerate particles to near light speed, bombarding the neighboring star with high-energy radiation. Over thousands of years, this relentless assault boils off the companion's outer layers, leaving behind a withered, ghostly husk. Some victims, like the star-orbiting pulsar Pulsar B 1957+20, have already lost over 90% of their mass, reduced to a charred cinder barely larger than Jupiter. And the pulsar isn't done yet. It continues feasting, siphoning away what little remains until eventually nothing is left but an echo of a star and a pulsar spinning alone in the void. What makes these systems even more fascinating is how they warp the very space around them. The evaporating material doesn't just vanish, it forms a shimmering cloud of plasma around the pulsar, like steam rising from a pot of boiling water. In some cases, like the Black Widow pulsar Pulsar J 1311-3430, this nebula glows intensely in gamma rays, creating a toxic halo visible across interstellar distances. The companion star, meanwhile, is so thoroughly cooked that it's distorted into a teardrop shape, stretched by the pulsar's gravity even as it's blasted apart. Yet there's a morbid beauty to this destruction. The same radiation that erodes the companion also lights up the surrounding nebula, sculpting intricate structures that astronomers can study for clues. Some black widows even produce eclipses when the charred remains of the companion star pass between the pulsar and Earth, blocking its radio pulses like a cosmic curtain. By measuring these eclipses, scientists can weigh the remnants down to the last scorched kilogram, tracking their slow annihilation in real time. What happens when the meal finally ends? The pulsar, now alone, may eventually fade into obscurity, its beams weakening as its spin decays. But for now, these systems serve as a stark reminder of the universe's indifference. Even among the stars, there are predators and prey, locked in a dance where only one partner walks away. Most neutron stars are born in the violent death throes of massive stars. But there's another, far rarer path to their creation, one that bypasses supernova entirely. Imagine two white dwarfs, the Earth-sized embers of dead stars, locked in a slow spiral toward each other. As they draw closer, their mutual gravity pulls material away, forming a swirling bridge of stolen matter. If their combined mass crosses a critical threshold, around 1.4 times the Sun's mass, the pressure at their cores ignites runaway fusion in a matter of seconds. But unlike a typical supernova, this detonation doesn't leave behind a black hole. Instead, the sheer force of the blast compresses the remnants into something new, a neutron star forged not from a single collapse but from the collision of two stellar ghosts. This scenario, known as a Type Ia supernova via double degenerate merger, is astrophysics' ultimate cosmic recycling program. The white dwarfs' already dense cores of carbon and oxygen are crushed beyond recognition, their matter fused into neutron-rich material in a heartbeat. The resulting neutron star often spins wildly, its rotation turbocharged by the angular momentum of the spiraling dwarfs. Some might even inherit a skewed magnetic field, twisted by the chaotic merger into configurations far stranger than those of supernova-born pulsars. What makes these merger-formed neutron stars unique is what's missing: the traditional supernova's explosive aftermath. When a massive star collapses, it ejects vast quantities of heavy elements into space, enriching future generations of stars. But white dwarf mergers often leave behind cleaner remnants, with less debris and a more symmetric environment. That's why astronomers hunt for neutron stars nestled inside, supernova remnants, or floating alone in empty space as potential candidates for this unusual origin story. Yet the rarest outcome of all might be the failed merger, where the combined mass teeters just below the threshold for total collapse. Instead of detonating, the two white dwarfs could merge into a single, unstable hybrid, a bloated, rapidly spinning object called a super-Chandrasekhar white dwarf. Over millennia, this Frankenstein star might slowly cool and contract until finally, it too collapses into a neutron star, a delayed rebirth after an eons-long dance. Whether born from instant catastrophe or slow decay, these merger-made neutron stars challenge our assumptions about stellar life cycles. They prove that death isn't always an end. Sometimes it's just the universe's way of shuffling the deck, dealing out new cosmic players from the remnants of the old. Deep inside a neutron star where pressures crush atoms into oblivion, matter doesn't just behave strangely, it becomes supernatural. At these unimaginable densities, protons may align into rivers of electric current that flow without resistance, while neutrons swirl like frictionless whirlpools, untethered by the drag of ordinary physics. This isn't science fiction, it's the cutting-edge theory of superconductivity and superfluidity in neutron star cores, where the rules of quantum mechanics twist into forms we've only glimpsed in lab experiments lasting fractions of a second. Take protons first. Packed tightly in the star's inner layers, these positively charged particles could pair up via quantum interactions, forming a superconducting fluid capable of carrying electrical currents with zero energy loss. On Earth, superconductors require ultra-cold temperatures to function, but inside a neutron star, the sheer density alone might force protons into this state even at millions of degrees. The implications: a perpetually churning dynamo that amplifies and sustains the star's magnetic field, like a cosmic electromagnet with no off switch. Some researchers speculate this could explain why magnetars develop fields 1,000 times stronger than ordinary pulsars. Their superconducting cores might act like giant amplifiers, twisting and stretching magnetic field lines into knots of unimaginable power. Then there are the neutrons. In the star's outer core, these uncharged particles could transition into a superfluid, a frictionless quantum liquid where particles move in perfect lockstep, like a school of fish turning as one. Unlike earthly superfluids, which require temperatures near absolute zero, neutron star superfluids thrive in the furnace of extreme pressure, their behavior dictated by the mind-bending rules of quantum mechanics at macroscopic scales. When a glitch suddenly speeds up a pulsar's spin, it might be the superfluid's doing. Vortices in this bizarre fluid, normally pinned to the crust, could suddenly break free and transfer angular momentum outward, giving the star a rotational kick. The interplay between these two states could rewrite how we understand neutron star dynamics. Superconducting protons might channel magnetic energy into concentrated zones, creating the unstable hotspots that trigger magnetar flares. Meanwhile, superfluid neutrons sloshing against the crust could generate starquakes, tiny fractures that release energy in X-ray bursts. Even the star's cooling rate holds clues. Superfluids conduct heat so efficiently that their presence would explain why some neutron stars cool faster than models predict, as if their interiors were tapped into a cosmic refrigeration system. Yet for all the theories, the truth remains locked beneath kilometers of impenetrable crust. Laboratories on Earth can recreate quark-gluon plasma for milliseconds, but neutron stars sustain these exotic states for millions of years. Every glitch, every magnetic anomaly, is a cipher waiting to be decoded, a message from a realm where matter sheds its familiar guise and becomes something entirely new. Until we can peer inside, these ultra-dense enigmas will keep challenging our understanding, proving that even in death, stars harbor the universe's most extraordinary secrets. Hidden in the depths of neutron stars might be one of the universe's greatest secrets, an invisible fingerprint of dark matter. Scientists have long suspected these ultra-dense objects could act as cosmic traps, capturing elusive dark matter particles that otherwise slip through ordinary matter like ghosts. If true, this would turn neutron stars into nature's most sensitive dark matter detectors, their unimaginable gravity acting like a galactic fishing net for particles we've never directly observed. Here's how it could work. Dark matter, which makes up 85% of the universe's mass, barely interacts with normal matter except through gravity. But a neutron star's gravitational pull is so intense that even weakly interacting particles would get snagged as they pass through. Over billions of years, these trapped particles could accumulate in the star's core, colliding and annihilating each other in a slow burn that releases energy. This extra heat would subtly alter how quickly the star cools, a thermal signature astronomers might detect by comparing neutron stars of similar ages. Some models suggest certain stars could cool slower than expected, their dark matter fuel keeping them artificially warm long after they should have faded into darkness. The search for this effect is already underway. Teams are analyzing X-ray emissions from isolated neutron stars, hunting for anomalies that can't be explained by ordinary physics. One tantalizing candidate is the nearby neutron star RxJ0720, 3125, which shows unexpected temperature variations that some theorists argue could hint at dark matter interactions. Others are studying pulsars in dense regions like the Milky Way center, where dark matter is thought to cluster, for unusual spin-down rates or glitches that might betray an invisible influence. But the implications go beyond detection. If dark matter particles get dense enough in a neutron star's core, they might trigger a phase transition, reshaping the star's interior into an exotic hybrid of ordinary and dark matter. Some speculative models suggest this could produce dark stars, objects with bizarre properties like hidden magnetic fields or even hollow cores. Others propose that accumulated dark matter could destabilize older neutron stars, leading to sudden collapses or quiet disappearances as they're consumed from within. Of course, not all researchers are convinced. Alternative explanations for anomalous cooling, like unusual superfluid behaviors or magnetic field decay, could mimic dark matter's effects. That's why scientists are refining their models, simulating how different dark matter candidates from WIMP to actions would behave under neutron star conditions. Future gravitational wave observatories might even hear the echoes of dark matter's influence, as subtle tremors in space-time reveal particles interacting where no light can reach. What's certain is that neutron stars offer something no underground lab can: natural experiments running for billions of years under conditions we'll never replicate on Earth. Whether they're silently collecting dark matter or hiding even stranger secrets, these cosmic extremes remind us that the universe's greatest mysteries might be lurking where we least expect them, written in the invisible ink of gravity itself. Just when we thought magnetars had reached peak weirdness, the universe serves up their polar opposites, neutron stars, with behavior so baffling they've earned the nickname anti-magnetars. These cosmic oddballs spin slower, shine brighter in X-rays, and most perplexingly have magnetic fields thousands of times weaker than their magnetar cousins. Take SGR 0418 plus 5729, discovered in 2009. This neutron star occasionally erupts in magnetar-like bursts, yet its surface field measures a mere several trillion Gauss, barely stronger than a typical pulsar, and a far cry from a magnetar's quadrillion Gauss monsters. So how does something with relatively weak magnetism mimic the violent outbursts of its ultramagnetic siblings? The answer might lie beneath the surface. Some theorists propose these objects are actually aged magnetars whose external fields have decayed over millennia, while their internal magnetism remains locked in the crust like a coiled spring. When that pent-up energy suddenly releases through crustal fractures or superconducting fluid disruptions, it triggers explosions identical to those seen in young magnetars, despite the tame exterior readings. It's like finding a retired boxer who can still throw knockout punches without seeming to flex a muscle. Other anti-magnetars, like Swift J1822, 1606, add another twist. Their spin-down rates don't match their measured magnetic fields at all. Normally, a neutron star's rotation slows predictably based on its magnetic braking, but these objects decelerate as if gripped by invisible hands. One explanation: their true magnetic energy might be buried in complex, twisted field geometries that standard models can't detect, like a hidden labyrinth of magnetism swirling beneath the surface. The implications are profound. If magnetic fields can hide inside neutron stars, our entire understanding of how these fields evolve over time might need rewriting. Traditional theories assumed fields decay steadily as stars age, but anti-magnetars suggest the process is messier, with exterior fields fading while interior ones persist or even regenerate through quantum mechanical effects. Every newly discovered anti-magnetar is a reminder that when it comes to neutron stars, the universe loves throwing curveballs, and that what we can measure might just be the tip of a very strange iceberg. Some neutron stars don't just flash their beams into the void, they listen for the echoes. Picture a bat in a cave, emitting chirps and mapping its surroundings by the returning sound. Now imagine that bat is a hyper-dense stellar corpse. Its chirps are bursts of X-rays powerful enough to sterilize planets, and the cave is an interstellar nebula light years across. This is the bizarre reality of echoing neutron stars, where fleeting X-ray bursts bounce off cosmic dust and gas like cosmic sonar, revealing hidden structures we'd otherwise never see. Take the neutron star XTJ 1550-564. In 2002, astronomers observed its X-ray flares not just arriving directly, but also returning as faint, delayed signals minutes to hours later. These weren't random echoes, they traced exact paths through space, having ricocheted off dust clouds hundreds of light years away. By measuring the time delay between the original burst and its echoes, scientists could triangulate the location of these invisible clouds, mapping their shapes and compositions with precision. It's like hearing a shout bounce off a mountain in pitch darkness and knowing instantly how far away it is, except here, the mountain is a nebula and the shout is a pulse of energy hotter than the sun's core. What makes these echoes so valuable is what they reveal about the interstellar medium, the thinly spread gas and dust between stars. Normally, this material is nearly impossible to study directly, too faint and diffuse to observe. But when a neutron star's X-rays blast through it, they ionize atoms, temporarily exciting them to glow in specific wavelengths. The resulting echoes act like a chemical fingerprint, exposing the nebula's composition. Some echoes even carry the imprint of magnetic fields, their polarization twisted by interactions with the dust, a detail that lets astronomers map the invisible magnetic skeleton of our galaxy. The parallels to sonar run deep. Just as submarines use sound waves to navigate murky waters, astronomers now use X-ray echoes to explore the Milky Way's hidden geography. In 2020, researchers analyzing echoes from the neutron star Circinus X1 discovered a previously unknown dust cloud 60,000 times farther from the star than Earth is from the Sun, a structure so distant and faint it would have remained invisible without the star's outburst lighting it up like a cosmic flashbulb. But there's a twist. These echoes aren't just passive reflections. The energy they carry can reshape the very clouds they bounce off, heating dust grains or even triggering new rounds of star formation in their wake. It's a two-way interaction where the neutron star doesn't just observe its environment, it alters it, leaving an imprint that lasts long after the echoes fade. So while these X-ray sonar pings might seem like mere curiosities, they're transforming how we see the galaxy. Every returning echo is a message in a bottle, carrying secrets about the invisible structures that fill the space between stars and the violent, radiant objects that help us find them. Sometimes the universe's greatest discoveries come when we're not even looking for them. In 1967, a 24-year-old graduate student named Jocelyn Bell was reviewing data from a new radio telescope in Cambridge when she spotted something bizarre, a series of precise, repeating pulses arriving every 1.337 seconds with clockwork regularity. The signal was so unnervingly artificial that her team jokingly labeled it LGM1, short for Little Green Men. For a brief, thrilling moment, they wondered if they'd stumbled upon evidence of extraterrestrial intelligence. But the truth was even stranger. Those pulses weren't alien transmissions, they were the first detected heartbeat of a pulsar, a rapidly spinning neutron star beaming radiation across space like a cosmic lighthouse. The discovery shattered assumptions about what existed in the universe. Until then, neutron stars had been purely theoretical, ghostly remnants predicted by physicists but never observed. Now here was proof, an ultra-dense stellar corpse, no larger than a city yet spinning faster than a kitchen blender, its magnetic poles sweeping beams of radio waves across Earth with metronomic precision. Yet Bell's breakthrough was shadowed by controversy. When the Nobel Prize in Physics was awarded for the pulsar discovery in 1974, it went not to her, but to her thesis advisor Anthony Hewish and astronomer Martin Ryle. The oversight sparked decades of debate about scientific credit and gender bias in academia. Bell herself remained gracious, but the episode highlighted how easily unrecognized labor, especially by junior researchers and women, could be overlooked at the highest levels of science. What makes this discovery even more remarkable is how close we came to missing it entirely. the pulsar signal was faint, buried in thousands of feet of paper chart recordings that Bell manually scrutinized. Her persistence in noticing an odd bit of scruff on those pages, and her curiosity to investigate rather than dismiss it, changed astronomy forever. That first pulsar, now known as CP1991, opened the floodgates. Within months, more were found, proving neutron stars weren't rare flukes but common cosmic endpoints. Today, CP1991 still pulses away, quieter but no less precise, a testament to both the universe's capacity for wonder and the human tenacity required to uncover it. Bell's story reminds us that sometimes the answers we find are far more extraordinary than the ones we seek, and that science's greatest chapters often begin with someone willing to question the scruff others ignore. For decades, fast radio bursts, those bizarre, milliseconds-long blasts of cosmic radio waves, have been one of astronomy's greatest puzzles. These eruptions pack more energy than the sun emits in months, yet vanish before we can blink, leaving no trace of their origins. Then, in April 2020, everything changed. A magnetar named SGR 1935+215, lurking in our own Milky Way, erupted with a radio burst so powerful it temporarily deafened telescopes around the world. For the first time, we'd caught a neutron star red-handed in the act of producing one of these mysterious signals. What makes this discovery so groundbreaking? It's the closest thing to a smoking gun we've ever had. Before this, all known FRBs came from distant galaxies billions of light-years away, their signals stretched and scattered by cosmic expansion. But SGR 1935+215 was right in our backyard, just 30,000 light-years distant, allowing astronomers to study its outburst in unprecedented detail. And the match was uncanny. The burst's duration, frequency spectrum, and even its polarization mirrored those of cosmological FRBs, suggesting magnetars might be behind at least some of these enigmatic events. But here's where it gets complicated. While this magnetar's burst was powerful, it was still 1,000 times weaker than the average extragalactic FRB. That discrepancy hints that something even more extreme might be needed to explain the most energetic examples. Perhaps a magnetar in the throes of a cataclysmic starquake, or one orbiting a black hole in a deadly embrace. Some repeating FRBs, like the famous 12 billion light-year distant source FRB 1211-2, pulse with clockwork regularity, suggesting they're tied to neutron stars in binary systems where tidal forces or accretion flows trigger periodic eruptions. Others might arise from Pulsars, a hypothetical neutron stars so massive they teeter on the edge of collapse into black holes, their death throes unleashing one final catastrophic burst. The implications ripple far beyond mere curiosity. If neutron stars are the engines behind FRBs, their signals become cosmic tools. As these radio waves traverse intergalactic space, they interact with the sparse electrons between galaxies, carrying encoded details about the universe's large-scale structure. Some FRBs even exhibit scattering, where their signals arrive slightly smeared in time, a fingerprint of the turbulent plasma they've traversed. By decoding these distortions, astronomers can map the universe's missing matter, the diffuse gas that's invisible to telescopes but makes up half the atoms in existence. Yet the mystery isn't fully solved. The diversity of FRBs, some one-off explosions, others repeating like celestial metronomes, suggests multiple origins might be at play. Magnetars could explain the repeaters, but the most violent single bursts might still stem from rarer events, like neutron stars colliding or black holes shredding their stellar companions. What's certain is that these fleeting signals have turned neutron stars from curiosities into cosmic lighthouses, their brief, brilliant flashes illuminating not just their own nature, but the vast, unseen web of the universe itself. Every burst is a new clue waiting to be deciphered. Neutron stars aren't just remnants of stellar explosions, they're cosmic time capsules, preserving the violent conditions of their births like fossils locked in space. Every spin, every magnetic field, every glitch holds clues about the star that came before them, offering a window into the lives and deaths of the universe's most massive stars. Think of them as celestial archaeologists carrying the DNA of their origins in their very structure. Take their rotation speeds, for example. A neutron star's spin is a direct inheritance from its progenitor. When a massive star collapses, its core contracts, and like a figure skater pulling in their arms, it spins faster, conserving the original star's angular momentum but compressed into a tiny, city-sized package. By measuring a pulsar's spin today, astronomers can reverse engineer the dynamics of the star that created it, estimating how fast it was rotating before its catastrophic end. Some neutron stars, like the millisecond pulsars whirling hundreds of times per second, might even carry hints of a past life as part of a binary system, where they stole material and angular momentum from a companion star. Then there's their magnetic fields, fingerprints of the chaos during their birth. A neutron star's magnetic strength depends on the original star's core dynamics and the turbulence of the supernova explosion itself. Magnetars, with their off-the-charts fields, suggest a particularly violent collapse where magnetic lines were twisted and amplified to unimaginable levels. Meanwhile, quieter neutron stars with weaker fields might have formed from stars that exploded more cleanly without the same magnetic turmoil. By studying these variations, scientists can piece together a taxonomy of supernovae, classifying stellar deaths by the neutron stars they leave behind. Even their composition tells a story. The heavy elements forged in a supernova, gold, platinum, uranium, are sometimes trapped in the neutron star's outer layers or ejected into space to later become part of new stars and planets. The presence of certain elements in a neutron star's spectrum can reveal details about the chemical makeup of its parent star, like a cosmic ancestry test. And when neutron stars collide, as in the kilonova observed in 2017, they scatter these precious metals across the galaxy, seeding future generations of celestial bodies with the building blocks of planets and maybe even life. Perhaps the most remarkable thing about these stellar relics is their longevity. A neutron star's extreme density means it cools slowly, preserving its internal heat for billions of years. That makes them time travelers of a sort, objects that can outlast most stars in the galaxy while retaining the physical imprints of their explosive origins. Some of the oldest known neutron stars, like Pulsar J 2144-3933, have been spinning quietly since before Earth formed, their steady pulses carrying whispers from an era when the universe was young. So while we might never witness a supernova up close or watch a star's core collapse in real time, neutron stars give us the next best thing, a fossil record written in gravity, spin, and magnetism. Every pulse, every burst, every ripple in space-time they create is a message from the past, a reminder that even in death, stars find ways to speak to us across the eons. From their birth in supernova that outshine galaxies to their silent decay into darkness over billions of years, neutron stars have proven themselves the universe's ultimate extremists, cosmic laboratories where matter, gravity, and time itself are pushed past breaking point. We've explored how these stellar remnants pack suns into cities, spin faster than kitchen blenders, and warp space-time into funhouse mirrors. We've witnessed their magnetic fields rip atoms apart from light years away, their collisions forge gold by the planetary ton, and their gravitational whispers reveal secrets about black holes, dark matter, and the fabric of reality. Some defy logic with starquakes that crack planetary crusts, while others hide oceans of free-floating quarks in their cores, matter so exotic it hasn't existed since the Big Bang's first second. They serve as nature's most precise clocks, yet occasionally glitch like broken timepieces, hinting at quantum chaos beneath their surfaces. They vaporize companion stars in deadly embraces, then hurl their ashes across space in jets near light speed. And in their quietest moments, they become cosmic archaeologists, preserving the fingerprints of their violent births across eons. Yet for every mystery solved, every pulsar timed, every magnetar flare catalogued, neutron stars leave us with 10 new questions. What lurks in their impossible cores? Could strange matter truly rewrite physics? Why do some burst with radio waves while others scream in gamma rays? Each discovery peels back another layer, revealing just how much we've yet to learn about these gravitational monsters. So now we turn to you. Which fact shattered your expectations the most? Was it the teaspoon of neutron star material weighing 1 billion tons, the ancient pulsar spinning since before Earth formed? Or the mind-bending possibility that dark matter might be silently collecting in their cores? Drop your favorites in the comments and let us know what cosmic mystery we should explore next. Because if there's one lesson neutron stars teach us, it's this: the universe is always stranger, wilder, and more wonderful than we imagine, and the next revelation is just a beam of light, a ripple in space-time, or a curious mind away. Stay hungry, stay awestruck, and keep looking up. The cosmos has only begun to show its hand.